So we have learned a lot in this class. I hope you guys feel like you have learned a whole lot about how stuff bends and twists and whatever. So far, we've learned how to deal with them in isolation. We've learned how to pull, we've learned how to push, we've learned how to twist, we've learned how to bend, we've learned how to lose your boat on the highway if the trailer hitch fails. That's not good. My husband once did have his boat pass him. The boat, something went goofy. I don't know if it bounced or I don't know, but the boat came up like he could see it. He's driving and there's the boat. It does sound like something from a cartoon, but all was well. There was no oncoming traffic. The boat just kind of scoot over into the ditch. Everything was good. Aluminum hull, so everything was happy. But yeah. Wow, how did I get sidetracked on that? Trailer hitch, right. So we've learned how to deal with these things individually. And if we think back to part 2, I believe is when we talked about this. We had these structures, they're axially loaded, and a couple of you, I believe, even sort of commented on the curiosity that it's the same structure. And if I slice it this way and think about what's going on in the glue, from that perspective, you have all normal stress. But if you slice it and have this scarf joint, you have both normal stress, because normal is always perpendicular to the cut, and shear stress. It's like, hang on, it's the same thing. You're just pulling on it. How is it different? And it's different because essentially you're looking at it with a different coordinate system. And so today we're going to learn how to build this coordinate transformation matrix and then show you why or how this coordinate transformation lets us add normal stresses and shear stresses. Okay, you don't really add them, but you rotate your world until one of them goes away. So at the end of last time, and there's still not a marker in here. Oh, wait, there it is. At the end of the sine problem, we ended up with a little hunk of material that had some shear stress acting on it, and it had some normal stress, and we said that's where we have to stop for now because that's all we know how to deal with. And by the end of today, this thing right here is called an arbitrary stress state. Arbitrary stress state. And by the end of today, we're going to understand how to figure out what's called the principal stresses. So that's the end game for today. And we're going to do this by learning how to transform stresses in these coordinates and find the coordinate system, the new coordinate system, that gives us what we call principal stresses. So put on your geometric seat belts because we've got a little bit of, I guess, graphical setup before we get to this transformation matrix. So plane stress, not like vanilla, but like flat on a plane. We've dealt with a very simplified case. We've dealt with one direction at a time, and in this lab we're going to deal with a plate for the first time, where we go from something that was long and skinny, beam, shaft, wire, whatever, we're going to deal with something that is flat or planar. But in the big, scary three-dimensional world, you have a lot going on, and you can have normal stress. If this is our little cube of stuff, you can have normal stress going on in 3 ways: sigma x, sigma y, sigma z. And then you also have 6 pairs of shear stresses. And shear stresses go along with a naming convention. This guy right here is shear stress on the x face in the y direction. So therefore, this guy has to be shear stress on the y face in the x direction. Then we've got another pair that's going to go here. So this guy is tau on the z face, gets too tight, in the x direction. And he has to have a friend to maintain equilibrium that would be on the x face in the z direction. And then we got one more set. Let's go with happy blue. Happy trees. So that guy would be YZ, and his friend is ZY. And this is only 3 of 6 faces. You got the same thing poking out the other side on the negative face of each, and I'm not even going to begin to try and draw that because it would be spaghetti. We have a few simplifications. Or I guess first, the mathematical construct that we make to make this sort of into a box that we can pick up and carry around a little easier from a computational standpoint is this thing called a second-order tensor. And that's basically meaning we're putting together a matrix of things that have magnitude and direction. So stress, the stress state is a second-order tensor, which means it's 3 squared values. And the important thing that we're going to take advantage of today is that we can do these coordinate transformations. Force and displacement are first-order tensors, meaning they have 1, 2, 3 elements as opposed to 9. And we can put these in this matrix. It's a diagonal matrix. My normal stresses are on the diagonal, sigma x, sigma y, sigma z. And I populate it so that it ends up being diagonal about those normal stresses. And because of equilibrium, like this red guy here, he has to be equal in magnitude to this red guy on this face. So we can make the simplification because if we're in this class, it means the sum of the forces is 0, and so they have to be. If they're not, it means things are dynamically warping. So we know that in this class, these 3 things are true. What else do we need? YZ is equal to ZY. So that simplifies things so that now that lower diagonal is equal to the upper diagonal. All right. So this is my full stress state. It's a 3 by 3 matrix. And we essentially aren't ever going to deal with this many quantities. We are always going to simplify down. I guess I want to write on here, not on the board. So we will very briefly look at a thick-walled pressure vessel, which does have 3 normal stresses: normal in the x, normal in the y, and normal in the z. It's actually hoop radial and axial, but we will very briefly deal with something that has all 3 stresses, but mostly we deal with things that are plane stress. Why do we call it that? Because it can be restricted to a single plane. What does that look like? It looks like sigma z equals 0, because that would poke out of the plane. And it also looks like, if you look back on your little drawing up at the top of the page, xz has to be 0, and yz has to be 0. Anything that has a component in that z direction, we say, nope, we're not going to deal with that. We're going to deal with stuff in the xy plane only. And that simplifies our life down to a very tidy 2 by 2. We're not so scared of 2 by 2 matrices. All right. So that's setting up the definition of plane stress is that everything is in our nice flat XY plane like this stress state. We've got a shear, tau xy, and we have a sigma y. We happen to not have a sigma x in this case. But generally, now switching gears to this coordinate transformation business. If we have our structure and we have an xy coordinate system, and just go along with me for a bit. If we want to change or rotate our coordinate system by some angle theta to a new one, and we'll call it x prime, y prime, there is math that will let us do that. We're saying we're moving it by an angle theta. So this is our stress state, that big prickly thing that we drew at the beginning. If we take out all of the z components, this is what we're left with. We're left with a sigma x, a sigma y, and a tau xy. So those are our components that fit in our nice little 2x2 matrix. And what we're going to do to set up this coordinate transformation is slice it on a plane that ends up with this little wedge. So we make our slice at the angle theta, and we're going to do a statics problem on our remaining wedge. So with our wedge, what do we have left that we know of? We didn't muck with the bottom, and we didn't muck with the sides. So we know we still have a sigma y down here, and a sigma x here, but we have a new one here that is in our new x prime direction. Similarly, we have an unbothered tau xy on the bottom and the back, and we must have a new tau x prime y prime along our new cut face. And again, the fact that this angle is theta lets us set this up. So this is shear stress on cut plane, and this is normal to cut plane in x prime direction. And according to our naming convention, this is stress in the y prime direction on the x prime face. Okay, but this drawing is what? This drawing is talking about stresses. What do I do statics problems with? Forces. If I have stresses, but I want forces, what do I need? I need to multiply by areas. So we're going to start by thinking about what our areas of these various faces are. If we call this width W, and we say, okay, along our cut face, we're going to call it unit length. So that is 1. It is 1 long. What is this area? It's 1 times W. All right. That guy's theta. If this guy is 1, what is this guy? Or this guy? This guy is sine theta, and this guy is cos theta. So the area of the bottom is therefore W sine theta. Everybody with me on that geometry? Maybe, kind of, sort of. Area of the back is then W cos theta. So then my forces have to be stresses times areas. So this normal stress here, this normal force here is the normal stress, which is sigma in the x prime direction, times that area. This guy is sigma y times w sine theta. And this guy back here is sigma x w cos theta. That deals with my normal stresses. Then my shears, we got this guy is tau x prime y prime times w. This force is tau xy w sine theta. And this guy, tau xy w cos theta.
You're multiplying those times the area?
Right, because what is a force, or what is stress? Stress is force over area. If I want forces, I need stresses times areas. Okay. Here's my areas, my stresses were up on the other one, so yes, I'm multiplying to get the forces. Now we got forces, we can do a statics problem, right? Sum of the forces, and at this point I'm going to move this guy over here and zoom down a little bit. And I'm going to get my other one over here. I'm going to zoom in a little bit. Whoa, not that much. Where are we? Here we are. Nope. Here we go. So we can do our statics problem, right? We can just add all these up. What's our problem with that? They're not all in the same direction. So we need some components. We need to break this guy and this guy into components all in the x prime, y prime directions. We're going to start with the normal stresses. So this guy's good. He's in the direction he's supposed to be. Sigma x prime w. And I'm going to draw the original resultant as a dotted line, because those are the ones that we need to resolve into components. So this guy is going to have a component this way and a component this way with my theta there. This guy is going to have a plus x prime, no, a plus y prime and a minus x prime. What are these magnitudes? This guy is sigma y w sine theta. So what is this component? This component is that magnitude times cos theta. And this component is the resultant magnitude times sine theta. Same thing for this guy, sigma x, w cos theta, and it's the adjacent, so another cos theta, and this guy, sigma x, w cos theta, and an opposite, so a sine theta. Lots of cosines and sines. Shear stresses. This guy's all right because he's in the x prime, y prime. Then this was the original, which is tau xy W sine theta. We need the components in the new direction. Same with this one. We'll have one component this way and one component this way, with that being our theta. So this guy, tau xy, W sine theta times cos tau xy, W sine theta, sine theta, tau xy, W cos theta, and that one is adjacent, so cos theta, and tau xy, W cos theta, sine theta. And I'm going to leave these up if you're a little lost in the coses and sines and coses and sines. It's posted, it's being recorded, but conceptually you see what's going on. We've made this, we've made our components in our new x prime, y prime direction, and now, finally, we are ready to do our statics problem. So I'm going to come back. No, I'm gonna leave that one there. I'm going to come over here, and I'm going to start with the shear stress terms. What are my forces? What's my sum in the x prime direction? What do I have going on in x prime? I got one of those, and I got one of those. And both of those are in the minus x prime direction. So I know I've got minus tau xy, and I've got a W cos theta sine theta, and I have a minus tau xy, W sine theta cos theta. But hey, those are kind of the same thing. So really I have two of that. All right. Now, if you look back at what's going on here, what all do I have in the x prime direction that comes from the that comes from the normal stress components? I have a plus sigma x prime w. Are you with me? Are you? Maybe? Yes? What else do I got?
Sigma y sine times something.
I got a w sine theta, sine squared theta, and that guy's negative. And what else? A minus sigma x w cos squared theta. Okay, so those are my three in the x prime direction here. So that's my statics problem. All that has to equal 0. The green and the purple is the sum of all my forces in my new direction. That has to equal 0. What do we see? Every term has a w, doesn't it? Get out of there. And what I really am interested in is what is the normal stress transformed into my new x prime direction. So I'm going to solve this bad boy for this sigma x prime. And that equals sigma x cosine squared theta plus sigma y sine squared theta plus 2 of these tau xy cross terms, cos theta, sine theta. It's just a cross term. There probably is a trig identity that you could do something with that, but we're going to chunk them all into a matrix so you don't need to make them be something else. All right, so now we need to sum everything in the y direction. So we're still in purple, so what do we got going on this guy in the y direction? Well, we got this guy. So we have a sigma x w cos theta sine theta. And we've got this guy down here, a minus sigma y w sine theta cos theta. Then, is that it for the y prime direction? Yeah. All right. How about our shears? What all we got going on from our shears? We've got a plus tau x prime y prime w. We have a plus this thing, plus tau, yeah, tau xy w sine squared theta. That's this. And then we have this one, which is this guy hiding up here, minus tau xy w cos squared theta. All of that equals 0. Well, our w goes away again. W, 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 w. And what can we do here in our new coordinate system? We get a tau x prime y prime. And we can say, oh, okay, that equals minus sigma x cosine theta sine theta. And a plus sigma y cos theta sine theta. And then plus tau xy times cosine squared theta minus sine squared theta. I know, it's a lot of coses and sines. But it came from the geometry and slicing it on that angle. So we have our normal in our new x direction. We have our shear in our new x prime coordinate system. Which one are we missing? Sigma y prime. How do we get sigma y prime? Well, we could do the same thing and cut it on a different angle and do the force balance, or we can be judicious about our trigonometric trivia. If you have something that is orthogonal, separated by 90 degrees, and you scoot one of them by theta, you know that the other one has to be at theta plus 90 because that's just being orthogonal. So I can be slick and say, oh, well, I know that cos of something plus 90 is minus sine of that thing. And the sine of something 90 degrees further around than the thing I have is just the cosine of the thing. Then that lets me write my sigma y prime as sigma x sine squared theta plus sigma y cosine squared theta minus tau xy times this cross term. And now, ladies and gentlemen, is the big ooh, ah, wow moment. Okay, not really, but this thing right here is the result of all of this craziness. This thing right here is the matrix form of these equations that we just wrote.
Are we still, is this still multiplied by 2, the tau xy?
Oh, yeah, I dropped a 2. Come back, 2. Oh, that's not. Yep. All right, so remembering how matrix math works, let's do this one for example. Sigma y prime equals something times sigma x. Well, that something is my sine squared, plus something times sigma y, my cos squared, plus, oh look, minus 2 cosine sine times tau. So that's our transformation matrix. And I know, you're like, okay, great. Why? What difference does it make? Hold with me, hold with me. So with this transformation matrix, which you can code up into Excel, which you can code up into MATLAB, which you can get something else to do the heavy lifting for you, you can take any given stress state, and if I say rotate this stress state by 45 degrees, you can go, okay, Captain, and you can plug it into the transformation matrix, and it gives you new stresses. Again, you're like, okay, why? This is why. Well, let's do an example first. If I say, here's a stress state, rotate it by 30 degrees, what do? You put in your old stress state. You put in your old stress state. You put in your old stress state here, and you do the math, and you get a new stress state here. So here's an example where we have, okay, sigma x is 8,000. So this one's going to look a little different. So we have a plus 8,000 here and minus 3,000 here. And there's a tau xy missing. And tau xy equals 6,000. Now remember your sign convention on shear stresses. How do I know which way to draw these arrows? That plus 6,000 mean it's on the plus x face in the plus y direction. So it is an up arrow. And if I have an up arrow here, that means I have to have the arrow this way to keep it in equilibrium. So this is tau xy equals 6,000. So this is the picture of what the stress state, this is called an arbitrary stress state. This is the drawing of that. And I say, okay, rotate it by 30 degrees. And so you plug in your numbers here, you do 30 degrees in there, and again, you let whatever your favorite matrix doing tool is do the work, and you end up with 10,446 minus 5,446 minus 1,763. Okay, so what? Well, so what is this what? It started out looking like this one. Where we had 8K, 3K, and 6K. And then we rotate it by 30 degrees. And now we have 10.5K, we have 5.4K, and our stress now changed sign. The shear stress changed sign. So this now is a shear stress of 1.7K. But it's the same structure under the same loading. So if I went from a plus 6K here, and I rotated it through 30 degrees, and I end up with a minus 1.7 here, what had to happen in the course of that? This went from plus 6 to minus 1.7. What happened? At some point it was 0. And 0 is an important place to be when you're shear stress. So if I jump ahead, where am I? Is the next thing in your course pack the little plot? All right. This is a powerful plot right here. And mine's in color, so it's better. Okay, if we call our starting space, starting point, theta equals 0. Shake it off, Taylor. Stay with me. Theta equals 0. What do I have? I have sigma x was that number, right? Sigma y is my dotted line. or yeah, is my dotted red, and my tau of plus 6,000. And this is now plotting what happens to each of these quantities as I rotate through 180 degrees. How far did I happen to rotate it this time? I said, oh, let's do 30 degrees. What happens when I go through 30 degrees? I end up about here, and what values did I end up at? At 30. I bet they end up being these numbers out of the matrix. 10, 4, 4, 6. Don't take the red pill. Minus 5, 4, 4, 6. And minus 1, 7, 6, 3. So if I rotate through that 30 degrees, I get those values. If I rotated through a little less than that, you end up with maximized sigma x and minimized sigma y. So what are some important things before we do any more sort of math? What are some important things that we see out of this?
We said that the max is sig x and sig y.
Mm-hmm.
At that point.
Yup. So in this case, at about theta equals 25 degrees or so, we have a max in sigma x prime and a min in sigma y prime. If you then go 90 degrees from that, what happens? At theta equals 25 plus 90, the opposite is true. You get a big sigma y prime and a minimum sigma x prime. Opposite is true. And then what did you say? You said that when sigma x prime, sigma y prime are either the max or min respectively, what's the other important thing? Tau x prime y prime equals 0. When do we have a maxima or a minima in tau? It's at 45 degrees rotation from that. And what's significant when I have a tau maxima, extrema? Those guys are equal. Those guys are equal. So where tau x prime y prime is a max or min, sigma x prime is equal to sigma y prime. And that happens 45 degrees from your max normal stresses. So there's a whole lot of important possible things going on this plot, because we now know how to transform these stress states and see what the maximum values are. So still, do we see how this lets us add sigmas and taus yet? If I say, here is my stress state, I can then ask the question, on what planar orientation does my worst normal stress happen? Well, in this case, it's at 20-something degrees. So that's the worst case normal stress. What's my worst case shear stress? Here. And what's that value? It's that value. And those values, either our tau max or our principal stresses, those are the ones that we use in the failure criteria. Because if you, and think about it in terms of like the wood. If you innately know that wood is stronger this way than that way than the other way. So if you pull on a piece of wood, it's going to fail in the orientation that it's weaker. No matter how you apply the forces, its weak orientation is the one that's going to fail. Now, instead of my material being direction sensitive, we can rotate our coordinates to figure out where the worst case in an isotropic, if we have aluminum or something that isn't preferentially directional, we still figure out what our worst case is. So how do we do this? Got one more page. How can we figure out, and this is a calculus question, how do we figure out where this happens? Where in theta? What angle? Take a derivative, set it equal to 0. So if we maximize this guy, where'd we go? Here we go. So if we want to find the location of my maximum sigma x prime, what do? I want to find the theta. So I take a theta derivative and set it equal to 0. That's where my trig identities are going to come in, because you get derivatives of sines and cosines and you get all kinds of craziness, and we're not going to go into that detail. We are going to cut to the answer, because it does get a little icky. So we're going to cut to the answer, and the answer is theta sub A. We're going to call it A for the location of the maximum. And it is equal to 1/2 the inverse tangent of the untransformed shear stress divided by the difference, half of the difference, of the original normal stresses. And I guess I need to finish that parentheses. And then the other angle, you already know where the other angle is. If I go back over here, if I figure out where this one is, where is this one? 90 degrees further. So if this one is that, then theta B is theta A plus 90. All right. Then how do I know what value this is? I now know where it happens, and it happens at theta A. So how do I know what my value is? I sub theta A into this thing up here, and I end up with my two principal stresses. So this is a new term, new terminology, new subscript soup, sigma A and B. Those are your principal stresses. This is an arbitrary stress state where you have a sigma x, a sigma y, and a tau xy. Sigma x, sigma y, and a tau xy. You are going to transform it, or you're going to figure out where your principal stresses are, and you will get sigma A, sigma B are your principal stresses, A and B. And the actual answer is the mean. No, that's a Y. The mean of your original stresses, normal stresses, plus or minus this difference squared and the shear stress squared. This thing right here is the basis for this graphical method that we're going to learn that is more circle. So that looks sort of like a Pythagorean distance. That's the radius of our circle. This is an average value, and we're going to learn how to do that on Monday. So very important, put stars and like flashing lights on the fact that this thing under this square root is not this thing. This is the average value. This is half of the difference. There's a minus sign in there. Very common fumble. So that's the value of the principal stresses. And another note, depending on the reference you're using, you may see sigma A's and B's, you may see sigma 1s and 2s. In here, sigma 1s and 2s are different from sigma A's and B's. And you'll, again, learn that on next Monday and Wednesday. Sigma A's and B's are the ones that we're starting with now, but some other texts use different notation. So what are the numbers? If this was our stress state and we had our little tau xy that we forgot about, what are they? Sigma A and B equals, what do we need to do? We need to do sigma x plus sigma y, don't lose your signs, average, plus or minus the square root of sigma x minus, don't lose your negative sign, sigma y over 2, that thing squared, plus tau xy squared. Do math. 2,500 plus or minus 8139, which ends up being 10,639 minus 5,639. What are these things called? Ding, 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 ding. Where do they happen? They happen at 1/2 the inverse tangent of sigma x, no, tau xy over this difference. It's a lot of parentheses. And it ends up being 23 3/4 degrees. Where is the other angle? Theta B is at that plus 90, 113 3/4. So that is principal stresses. That is stress transformation. It's an abstract one to wrap your head around in terms of, okay, we're just going to spin our world around and find out what's the worst case scenario. That's essentially what you're doing. And that's that. Wednesday we talk about pressure vessels. This week's lab is pressure vessels.